Assalamualaikum and greets to the viewer and Dr. Nurhaniza, that is lecturer for our course. So this is a group project presentation which is methanol water separation process. Okay, so next is introduction. So flash distillation is a single stage separation process that are commonly used in chemical engineering to separate liquid mixture based on difference in volatility. In this experiment, a methanol water mixture is studied because methanol is more volatile than water and therefore tends to vaporize more easily during the flashing process. So when the feed is subjected to a sudden pressure drop or temperature change, partial vaporization occurs, resulting in the formation of a vapor phase arranged with methanol and a liquid phase with water.
First, for our objective, to design a flash for separating mixture, that is for methanol and water. Second, to review the processes and typical process condition, overall composition, operating pressure, and also temperature. And lastly, calculate the moles of liquid, moles of vapor, liquid phase mole fraction, and vapor phase mole fraction.
So this is a overall process flow diagram or PFD that we do a research.
On this slide, I explain the process condition and feed composition used in flash distillation process. The feed consists of methanol water mixture with an overall composition of 0.5 mole fraction methanol and 0.5 mole fraction water. The operating pressure is 101.325 kPa and the temperature is 82.38 degrees Celsius. Methanol has a boiling point of 64.7 degrees Celsius, while water has a boiling point of 100 degrees Celsius. Since methanol has a lower boiling point, it is more volatile and vaporizes more easily than water during flash distillation. This difference in volatility is the main principle used to separate the two components. Next, I will explain about the assumption used in our calculation. First, the methanol water mixture is assumed to behave as an ideal solution. Second, the basis of calculation is 100 mole per hour of feed entering the flash distillation column. Third, the process is assumed to operate at 100% efficiency. That is meaning no loss occur during separation. And then finally, the system is assumed to be operating at steady state, where all processes are variable remain constant with time. All of these assumptions simplify the calculation and allow us to analyze the separation process more easily.
My name is Akif Naim bin Kamis. Okay, so for the flash calculation, we have 4 assumptions. First, the methanol water mixture is an ideal gas solution. Second, our basis is 100 mole per hour of the methanol water mixture into the flash distillation column. So the third, the process was operated with 100% efficiency. So for the last, our operation in a steady state. For the next slide, we have an overall process flow diagram, PFD. So our composition basis is 100 mole per hour of the reaction mixture. So for the methanol, we have a 0.5 mole and water is a 0.5 mole. So for the upper is a mole fraction in a vapor phase, and the bottom is a mole fraction in a liquid phase. So for the temperature, we get from the sum of the methanol and water temperature, and we just divide by 2 as midpoint the temperature, and the pressure we use the 101.325 kilopascal. So first step for the calculation, we need to calculate the vapor pressure equation using the Antoine equation. Can refer from the table B.2. So for the substance, methanol and water, we can get for value A, B and C. So for the methanol, we have 60.5785, B 3638.27 and C is 239.5. And substance water for the A is 60.3872, B is 3885.7 and C is 230.17. So the both we use the temperature midpoint, which is 82.38 Celsius. So we just use the equation and get for the methanol pressure is 195.45 kilopascal and water is 52.19 kilopascal. For the second step, after we get the value of the vapor pressure, we need to calculate the K value for each substance. So we use the Ross law equation, refer from equation 13.16, which is K equal to Yi divided by Xi equal to Pi saturated divided by P, and our P is 101.325 kilopascal. So for the methanol, we just substitute the value from the vapor pressure. For K1, we get the 1.9289, and for the water, we get the value K is 0.5151.
Okay, after we already calculate the value of K for a substance, we continue to calculate mole of liquid and vapor phase. So we calculate this by using equation 13.106. By using this equation, we get N1 equal to 49.29 mole per hour and N2 equal to 50.71 mole per hour. Okay. After we got mole of liquid and vapor, we move to calculate the vapor mole fraction. So we calculate vapor mole fraction by using equation 13.105. Okay, so for methanol we got Y1 equal to 0.6616 mole, and for water we got Y2 equal to 0.3384. Okay, after that we continue to calculate liquid mole fraction by using equation 13.16. So for methanol, we got X1 equal to 0.3430 mole, and for water, we got X2 equal to 0.6570. Okay.
So I think that's all from us, Group 2. Thanks for watching.